have Juanita Pinzon speaking for us in Gauge Theory Virtual, and maybe I'll let her take it away.
Okay. Thank you, Dave, for introducing me, and thank you, the organizers, for having me, and also for accommodating my teaching schedule. That's the reason why we're doing it today and not the usual time. So thank you very much for that. So what I'm going to do today is I'm just going to tell you why toroidal homology spheres have SU2 representations. And this is joint work Ty Liedman and Raphael Sendner. And the paper is already on the archive in case anybody's curious. Okay, so what's the main result from today? Well, it's the title, right? If Y is a Z homology sphere and there is two torus in Y that is incompressible, then there exists a homomorphism from the fundamental group of Y to SU2 that is non-trivial. In fact, a little bit more is true. We want this, the image of this homomorphism is not going to be abelian, which from now on, I will call this irreducible. Okay, and so the strategy is to first look at the topology.
So Juanita?
Yes. Yes.
So non-abelian is the same as non-trivial, right, for integer homology spheres. Is that right?
That is absolutely true. That is absolutely true. Yes, in this case, right. Yes, I guess what I was thinking is that there's a more general conjecture, which is that if we have a three manifold that is closed, connected, probably irreducible, but I don't know if I need this. Actually, I don't think that's necessary. So if this is not the three sphere, then there exists a representation from the fundamental group of M into SU2. And so as an observation, so sort of like to add to what John was saying, if the first Betti number of the three manifold is positive, then we have a representation that we get by factoring through the abelianization, and then we can just send any generator to a matrix of this form. So, you know, anything that generates in anything that is non-trivial in first homology is going to go to a matrix of this form. And as long as our angle theta is non-zero, this representation is non-trivial. However, here we are using a representation whose image is abelian. And this is this is all up to conjugation, I should say. Not all of them have to be like that, but up to conjugation, I can assume that they get to send like that to that. Okay. But in the case, if we have we could also have not first homology be torsion. So for example, for length spaces, and still we have an abelian SU2 representation. But once I get to the world of integer homology spheres, then I want irreducible or not abelian, right? And it's equivalent. So what is known so far? Oh, I was actually, as I said, in the middle of writing something. So the strategy is look at the topology of a toroidal integer homology sphere. Then we will translate to some statements about instant on floor homology. And then we will further translate two statements about submanifolds of the pillowcase. Okay. Yeah, let's do that. So first of all, the topology of toroidal homology spheres. So if that's the case, then, oh, actually, let me change my notation here. Let me call this sigma. Sigma is going to denote my toroidal homology sphere. So sigma is going to be decomposed as the splice of two knots where each one of the three manifolds is an integer homology 3 sphere, and the knots have non-compressible, they're not boundary, they're boundary incompressible. And furthermore, as far as existence of representations, we can assume that each one of these knot exteriors are going to be irreducible. Let me look at my cheat sheet to see where I am. Yes. Okay, good. I also want my homologies, again, as existence of representations, then I also want to assume that this yi is SU2 cyclic, which in this case really means it doesn't admit irreducible representations. And so if I have this fact, this fact and this fact, then that's what's going to matter. That's what I'm going to try to translate to statements about instant on floor, and that's what's going to give me the existence of non-trivial SU2 representation. So I'm going to color code it. So that we keep track of what's happening. Okay, so so now the translation.
Sorry, Juanita.
Yes.
Just to be clear, this is BG. Is this a construction proof, or is this just a existence statement?
Oh, no. It's very much just as an existence proof. I am not going to tell you what they are. I don't know what they're going to be, as the theory is going to tell me that they exist.
Okay, thank you.
Yeah, in fact, like in this translation to instant on floor homology, it's just a game of, I'm not going to compute the instant on floor groups. I'm only, the only information that we need is it 0 or is it non-zero? That's it. And so, for example, 1, if there are no representations, then it means that, well, I have the in the ideal setting, the generators of the chain complex or the chain groups that give rise to the instant on floor homology groups are precisely the irreducible representations. Well, yeah. And if I don't have generators, then the homology is going to be 0, right? So then that's the way I translate. So now we have 0. And now for the other two are going to get translated into the homology group of 0 surgery along the knot being non-zero. Okay. So now I have, I started with just looking at what it means to be toroidal, and now I have statements of what the homology groups have to be. And so let me prove this second one, right? How did this go? So suppose by contradiction that this group is actually 0, or these groups, instant on homology is 0. Then we have the surgery triangle, in which I'm going to have this homology group, and then I'm going to have well, let me write it as 1/0. Maybe it doesn't matter if I make it big or not, but okay. So I am assuming, this is my assumption, right? So I am assuming that this is going to be 0. This is precisely why, and I am also, I am actually assuming, okay, actually this is a lie. 1, 2, and 3 get translated to that, because I do absolutely need 1. If 1 is true, then I am saying that this group is 0. And so as a consequence, the instant on homology of +1 surgery is going to be 0. But then this surgery triangle is true even when I change. Here I put any n, and here is any n +1. So really, +1/n surgery is going to be 0 for all n's. Great. How am I going to reach the contradiction? The contradiction comes by looking at this theorem of Cronheimer and Morocco. Which says that if I have a 3-manifold that is closed, irreducible, and has first Betty number equal to 1, then the instant on homology of this group is non-zero. So what is the closed irreducible first Betty number 3-manifold that I am going to connect to what I have on the left-hand side? Well, here we're going to use a result of Cameron-Gordon from 1983, or published in 1983, which is that if you do +1/4 surgery on your knot, then this is going to be isomorphic to +1 surgery on the 2-1 cable of the knot. Okay. Why do I care about this? Well, I can then use a similar triangle but now for surgeries on the cable. Here, well, let's use the same notation. Cable here, cable, and the cable. And so, again, so I already know that one of them is going to be 0. Actually, when n equals to 0, then this is again, then when n is equal to 0, you know what? It's enough to do it for n equal to 0. I don't need. This is the same one that I had from before. This is just the instant on homology of y itself. This is now the one that this one is now 1/4 surgery on k. So by assumption is also going to be 0. And so this forces this last one to be 0. But that contradicts the theorem, the theorem that we have here. There's the contradiction because 0 surgery on the 2-1 cable can be written as the knot exterior of the original knot in our original homology sphere union some surgery on a solid torus along a curve this curve. And this is Seifert fiber. And here is we have the topological assumptions about our knot complement. This is boundary incompressible and irreducible. So then this means that in fact, this zero surgery on K12 is irreducible and has beta number 1. So we get a contradiction. Okay. Questions so far?
Yeah, so Juanita, I have a question. This is BG. So this is sort of, I should have asked this at the beginning, but so doesn't Steve Boyer have results about integer homology spheres emitting representations to like SL2C and SU2? Could you not prove it that way using left orderability and foliations and/or foliations? I mean, I don't work in this stuff, so I don't know the details.
There is a
You know this
theorem by
better.
Raphael Zentner that any integral homology sphere admits an irreducible SL2C representation.
Yes, exactly. So thank you, Nikolai. Yes, the theorem of Raphael, and that's, you know, like that's sort of the reason we joined forces with him. Like Ty and I had been working on some results and we had some computations, but we really needed the work of Raphael to get to this point. And his work says that every homology sphere admits a non-trivial representation into SL2C, right? And then of course, SU2 sits inside SL2C. So you need to work a little more to get to SU2 from SL2C. So yes, so note, we do use Raphael's results, techniques, let's say, to promote to SU2.
Okay, but so what I had in mind was something a little more geometric group theory. I mean, I think there are some results about left orderability of groups that allow you to construct representations into SL2C using work by Steve Boyer.
So I'm
maybe
not
someone-
an expert on
you know
left
this?
orderability. I do know, so I think so.
Maybe PSL2R tilde, right? But
Oh, okay.
Additions into SU2 here. That's just a different group.
It's
Okay.
a lot, BG, it's a lot harder to, I mean, it's a lot harder to get, I mean, SL2C is.
Yeah, it's R, it's not C, you're right.
You know, there's a lot more places for elements to go, so to speak.
Yeah, okay,
I
sure.
mean, you know, for instance, you know, also all hyperbolic manifolds, more or less by definition, or it depends on your definition, the fundamental groups have not only irreducible, but faithful representations into SL2C. And you know, so, but you know, finding some, but that doesn't really help you directly find a representation in an SU2. So you need, I mean, so what Juanita is saying is you need to do something, you need to use some new techniques, or maybe, I guess we'll find out, adapt Raphael's techniques for how to somehow find them into SU2 instead. So they're sort of different kinds of problems.
Okay, thank you.
Right, but I think the question is fair, right? Like here we're talking about representations of a fundamental group, and there's a whole theory of left orderability, and so are they even remotely related? And I think, I mean, I don't know, actually I'm curious. I think that John, you mentioned something like this in one of your talks recently, but I don't know if actual work has been done in this direction.
Not as far as I know. I mean, if you don't have any non-trivial SL2 or SU2 representations, then you're an instanton L space. And so you'd predict that the fundamental group is not left orderable just based on the L space conjecture and the conjectural isomorphisms between all these floor theories. But I don't think anything concrete has been written down.
Okay. I like the question. I just don't even know how to tackle it. But where was I? Let me go back to my cheat sheet. Sorry. Aha. I think that now, oh, now we're actually ready to translate into the pillowcase. So, oh no, but maybe before that, it is also true that Raphael already proved that the splice of two knots in S3 does have irreducible SU2 representations. So, you know, on one hand, we are promoting Raphael's work from SL2C to SU2, but he had already said, well, actually, you know, like if you have a splice, then SU2 is fine. But the difference is that now we're just saying it doesn't really have to be S3. So for us, replace S3 by any SU2 cyclic homology sphere. Do they exist? Well, if you believe the conjecture, then no. So,
Yes.
Right. So maybe we didn't prove anything. Anyway, I think it's still a cool result. I think I still like the way things work. But so let's just translate to the pillowcase.
I mean, yeah, you don't need your work if you prove that conjecture, but that's a very hard conjecture. So.
Exactly. Yeah, but if at some point, you know, like if tomorrow somebody posts a proof of the conjecture in the archive, then this talk is obsolete. So, I hope nobody's planning on doing that. Otherwise, let's just stop here. Anyway, so the pillowcase. So let me just tell you what the pillowcase is, right? So this gets thrown around a lot. So if you look at the fundamental group of the two torus and look at all the representations into SU2, well, they're just going to be completely determined by where you send a meridian and a longitude. And so up to conjugation, I can assume that, I mean, because the group is abelian and all the abelian subgroups of SU2 are conjugate to the circle, this circle, then the image up to conjugation is going to be given by a representation of this form, right? And so then this tells me that I can parameterize the space of representations by the square from 0 to 2 pi. But then again, if I am working up to conjugation, if I conjugate, say, this representation, the representation given by alpha beta, by this element, then we get 2 pi minus alpha and 2 pi minus beta. And so really, then I can restrict to just this rectangle, where here I go from 0 to 2 pi, and here I go 2 pi. And furthermore, here I am making these identifications. And that's why it is called the pillowcase, right? Because when you glue everything together, it looks like a pillowcase. So furthermore, just let me, so these two lines are going to become very important. So let me just observe that here, what this means is that the meridian is going to be sent to minus the identity. Right, that's what pi does. And these ones, the meridian is going to get sent to the identity. Okay. So the first lemma is that if I have Y and SU2 cyclic integer homology sphere, and I have a knot K in Y, then the space of representations of the fundamental group of the knot exterior gets mapped. You know, we can just restrict to what happens in the boundary of the knot exterior. And this is the pillowcase. And this I'm going to just denote by R of K. So the image of this will stay away from the vertical lines. Right, so I am actually saying, right, so again, back to my color coding. If I have something that is SU2 cyclic, then this is going to stay away from that. And this is basically the proof follows from a computation of the twisted cohomology at the points 0, 0, and pi 0, right? So what's the proof? Let me just say it. If suppose by contradiction, that the image in the pillowcase of the knot exterior intersects the vertical lines. So then what I have is that here's my intersection point. but this set is compact, so then I should be able to find some other representations in the image that converge to that. And then you show that in this case, because you have, and it's right. So again, on this side, the meridian gets sent to the identity. So if you have a representation of the knot group that sends the meridian to the identity, so what you really have is a representation of the whole homology sphere, but we're saying there's nothing non-trivial, so it absolutely has to be this point. And on the other hand, if you look at what happens over here when you send the meridian to minus the identity, so then in that case, it's not really, what you're going to get is not a representation so you get a representation into SO3. But the obstruction to lifting to SU2 is an element of the first cohomology of Y with Z2 coefficients, but I have a homology sphere, so this is 0. So then again, I would have a representation, a non-trivial representation. So no, it's not going to happen unless it's this point.
Do you mean second? Isn't that just the second
Yes.
Whitney class? Yeah.
Yes. Yes. It's still true that it's 0, but yes, thank you, Dave. Okay, and then it's just a matter of computing the twisted cohomology at these 2 points, and then you're still going to see that all the degrees of freedom are going to come from the reducibles. So the reducibles are going to be mapped to this bottom line, and so that's it. So if you get so you can get these 2 corner points as the limit of representations of the knot group, but because there are reducibles. But so as far as irreducibles go, then nothing. So again, so to emphasize, we know that in an SU2 cyclic homology sphere, then the image of the representation space of the knot group is going to live in there. And then the next result that we need, right, going back to the color coding in terms of instanton groups. First, I have SU2 cyclic, and then I have this non-trivial representation instantons of zero surgery. So then the second one is the second result that I need for that does involve this, which is that, and this is a small promotion of Raphael's result from S3 to general homology spheres. The theorem is that if I have let me just put it this way. If I have, so K and not in a homology sphere, and precisely this, then let P and Q be these points in the pillowcase. So P is the point 0, pi, and Q is the point pi, pi. Every path C in the pillowcase joining P and Q intersects the image of the representations of the knot group. Okay. So then, here I have any crazy path that I can think of, and it is going to have to intersect the representation group of the sphere. And this is, so let me make it all the work that Raphael did with holonomic perturbations. And the way they can be seen in the pillowcase. Let's see if I can prove it at the end. But for now what we have is, so if we put everything together, then what we know is, so if we have Y as U2 cyclic, or 0 instanton homology, and we have non-zero homology groups for the zero surgery on K, then there exists a curve let's say path gamma that is in the image of the representation of the knot group, such that the class of this path in the first homology of the cut open pillowcase is non-zero. What do I mean by the cut open pillowcase? I mean cut along the vertical lines. So precisely the which we can do because we are assuming that we have SU2 cyclic. And so how do we prove this? This is a little bit of this is just a combination of what we had before and some Alexander duality arguments in for graphs in the two sphere. But in the end, so what we get is we do get something wrapping around. Actually, this is going to be our gamma. So how do we, so this is the existence proof, right? So proving that representations exist. Here's the proof. We have each. So let's recall what we had from the beginning. We have our toroidal homology sphere that is the union of, or the splicing of two knots. And here, what do I mean by splicing? I think I said it in words, but I didn't explicitly write it down. I mean that the meridian of the first knot gets identified with the longitude of the second one and the other way around. So let's say, well, this is the only example that I can actually draw. So this is the actual picture of the trefoil in S3. But what we had is that we have a curve that wraps around the pillowcase for both of them, right? In this direction, in the vertical direction. So I'm just going to have something that goes up a bunch of times, maybe in a weird way. Then what happens? So I'm going to use the pillowcase. This is the pillowcase that I am going to use. So from the perspective of the pillowcase of the first knot, because I am switching the roles of meridian and longitude for the second one, then here I have to switch, or so I would have to tilt it, right? I have to rotate it to the side. Well, rotate it to the side and then do the identifications, look at it in the correct way in the fundamental domain. And so that's what gives me, so now I get this other curve. So the idea is we have from one of the spheres, we have a curve wrapping around, say, vertically, and then another one wrapping around. One wraps around vertically and the other one wraps around horizontally. So they have to intersect at some point, right? There has to be an intersection point. And the intersection point is what's going to give me the irreducible representation. So going back to BG's question at the beginning, am I going to tell you what the representation is? Absolutely not. Absolutely not. I mean, and right, the example is a little bit misleading. If you do know if you can compute the representation space of a certain knot exterior, and you know the way it maps into the pillowcase, then yes, you can describe what the irreducible representation is going to be, but you don't have to, which has advantages given that it's not like we have a lot of examples of images in the pillowcase, images of knot exteriors in the pillowcase. Okay, and I think that's it. That's the way we get the representation. Are there any questions? I appreciate that, John.
I thought other people would join it.
Muting makes that a little less effective. Can you say a little bit more about Raphael, how he gets the homology class to be non-trivial of the gamma?
Yes. So yes. You mean this one or this one? Am I allowed to assume this one? This is the super hard one. So this one I can sort of tell you a little about that, but this one, it's, yeah, so which one, Dave, sorry.
Maybe both.
Both are interesting, but start with whichever you find
Okay.
more comfortable.
This is simpler, right? It's Alexander duality.
Yes. This is the one. So now, so if I am allowed to assume this one, then this is really so. So let the image in the pillowcase of the representation space of the node exterior. You can think of topologically embedded graph in the pillowcase, so in S2. And then, so let me call it gamma, just because that's the way Raphael calls it. And so then the idea is, since you have that every path in the pillowcase joining P and Q intersects the graph, then you know that then if you remove this graph from S2, P and Q are going to be different components. And then, and moreover, so this, if maybe let's just take a little neighborhood of this graph. So this is going to be a union of disks. And so if you take S2, like this complement and glue back all the disks except the ones that have P and Q, then you get, basically you get a cylinder, right? And so, and the cylinder is going to be, you can push the generator of this cylinder into gamma, and that's how he gets the curve that wraps around. So,
Okay.
something like that. And then to prove this hard theorem, what's behind this is kind of briefly, because I really cannot go into a lot of details. That's the wonder of having a collaborator that understands something really, really well. The idea is that if you have, for every path C that joins P and Q, on one hand, so you can get a perturbation of the CS function, the Chern-Simons function. And a curve another path from P2Q close to C, such that all of the let me remember, I have to use notation. Basically you relate the critical points of the Chern-Simons function with the perturbation, and this gets identified or gets a correspondence with the representations of the node exterior that intersect this C prime. And that's and I actually don't remember the rest of the argument, but I know that once you relate the generators of the instanton groups with intersection points here, then you know, like, the only way in which this is 0 is if the bottom one is 0, and then you get a contradiction with this assumption. Something along those lines. I apologize. I don't really remember the details.
And you show that that floor homology group is independent of the perturbation. Yeah.
Yes. Absolutely. Yes, but that one, I mean, yes, but you sort of already know that, right? Like, that's the same argument that you use to show that the instanton groups are independent of the metric. I mean, basically.
So that's a slightly different question. I mean, in particular, this gives you another proof of Raphael's result without using all this degree 1 maps business, right? If you have an integer homology sphere and you want to know whether it has a non-trivial SE2 representation, you might as well restrict to prime manifolds, and then you have hyperbolic, you know, toroidal, or ciphered fibered, right? And so if you're thinking about SL2C, you know, the hyperbolics have non-trivial representations. And, you know, you've shown that toroidal manifolds have non-trivial SU2, therefore SL2C representations, and ciphered fibered case is easier. Can you, but this is for integer homology spheres. Can you somehow adapt this argument to prove a result like for all 3 manifolds that have H1 very small, like order, I don't know, less than 5. There's some maybe finite set of manifolds, and outside of that finite set, all the other ones admit irreducible SU2 representations.
Oh, you mean so for all but a few?
Yeah, the ones you should be able to enumerate.
There exist.
Irreducible
What do you have?
SL2C representations. I don't want to, yeah, you can't deal with the hyperbolic case, but I mean, you know, consider toroidal manifolds, in other words, splices that aren't homology spheres. I mean, I think all of the SU2 cyclic ciphered fibered spaces, those things have been, yeah, those are classified. So, like, you know, what about toroidal manifolds where H1 has order 2, let's say? Can you adapt this argument to show that they all admit irreducible SU2 and therefore SL2C representations? Anyway, it's just a question.
Well, what do you want to use instead of? I mean, this doesn't make sense.
That's true, but I mean, maybe you could, you know, if you could show that if you could show that, you know, these are still like relatively controlled splices of knots, right? And you knew that these, the images in the pillowcases of these knot complements, the representation varieties, had curves of certain slopes. And maybe when you glue according to some other gluing that's not meridian, longitude, meridian.
But the problem is that, so this is the picture. This is the picture that Raphael drew in our paper. Right, and so I think this is, I don't, this part of the argument that you say, oh, there's no way you're going to have this intersection point, goes through showing that you have a non-trivial element here. So that's the first place where I see this argument failing. I don't know if, like this, I don't know if there's some extra magic that you can do to just get exact information of what the element is in H or in H2. So I don't know.
Yeah, maybe this is a good reason for trying to upgrade it to a result about I sharp, you know, like the splice, this toroidal manifolds can't be instant-on L spaces among, you know, the integer homology spheres at least. I mean, we know from Liam, Jonathan, and who's the other guy, Claudius's work, that, you know, if you have a toroidal manifold and H lower 1 is as order less than 5, then it's not an L space. So if you could prove that result in the instanton floor world, then you'd know that there had to be irreducible SU2 representations, at least when order is less than 5.
Yeah, I would have to go back. Oh, I'm not going to.
Anyway, so yeah.
Try to write down. Does anybody know how to spell Claudius' last name?
D-I-B-R-O.
Yeah, I know. I couldn't get that far.
Run out of room on the page.
Yeah, exactly.
Claudius. Yeah.
DIB.
Oh, thank you, Josh.
You know what I'm saying? What I'm saying is basically, if you could prove for I sharp the same things you can prove on the Haggard floor side, then you could conclude that I think this result, you know, something like among manifolds with H1 really small, say less than 5, then for all but like certain ciphered fibered manifolds, you have irreducible SL2C representations, something like that. But
you know, maybe we should talk about that more later. Let me think about it. Yeah.